Hello, this is Jana Ibrahim. In this video, we will discuss about amplification. Let's consider these situations. When you cannot hear the music from a radio, you turn up the volume. When the picture on your television is too dark, you increase the brightness setting. Note that in both cases, we are talking about weak signal and make it stronger by increasing its power level. The process of increasing the power of an AC signal is referred to as amplification, and the circuit used to provide amplification is called an amplifier. Amplifiers are widely used in audio, video, telecommunication systems, digital systems, biomedical system, and so on. In fact, we might find it difficult to find an electronic system that doesn't have any amplifier in it. In this video, we will learn how to analyze different types of amplifiers. We will discuss how amplifier properties such as gain, input impedance, and output impedance affect an amplifier circuitry. An amplifier has three fundamental properties, namely gain, input impedance, and output impedance. These three properties are combined to form a general amplifier model. All amplifiers exhibit a property called gain. Gain is a multiplier that exists between the circuit's input and output. For example, if the gain of an amplifier is 100, then the output signal is 100 times greater than the input signal under normal operating condition. Gain is usually represented using the capital letter A. There are three types of gain: voltage gain, current gain, and power gain. Note that the subscript in each symbol identifies the type of gain. Hence, the letter A with subscript V represents voltage gain, AI is current gain, and AP is power gain, and the type of amplifier used in a given application depends on the type of gain desired. Gain is defined as the ratio of an output value to its corresponding input value. Voltage gain, for example, can be defined as the ratio of output voltage to input voltage, or Vout over Vin. Hence, AV is equal to Vout over Vin. For example, we can determine the gain for the figure shown. Vin is 400 microvolt and Vout is 250 millivolt. From the AV formula, we can get the gain is equal to 625. Note that the gain has no unit. The output or input voltages do not determine the value of gain. In fact, the circuit component values of the amplifier determine the value of voltage gain. In this figure, the amplifier circuit with a specific gain is represented as the box in the middle between input and output of a certain system. Basically, inside of the amplifier, there is a circuitry that gives certain amount of gain to increase the value of the input. The gain under normal circumstances is constant. Thus, a change in the input to amplifier will result in a change of the corresponding output value, not the change of gain. Let's reveal what's inside the amplifier box. This is the general model of a voltage amplifier. Inside the voltage amplifier box, there is a circuitry arranged with the voltage control source AVV-in is in series with the output impedance Z-out. The value of this voltage source is a function of the input voltage V-in and the voltage gain of the amplifier AV. There are also input impedance Z-in that connects the input side and output impedance Z-out that connects the voltage AVV-in with the output side. When we add signal source and load to the amplifier model, the complete circuit will look like in this figure. Here we can see that solving the complete voltage amplifier circuit can be divided into two parts, the input part and the output part, each representing a complete separate circuits at the input and output. When an amplifier is connected to a signal source, the source sees the amplifier as a load. Hence, the input impedance Z-in of the amplifier is the value of this load. You can analyze this circuitry by using KVL approach. Assuming that the source resistance is in series with the signal source, hence by writing the KVL at the input side, we get minus Vs plus I in Rs plus I in Z-in equal to 0, and from there we can derive input current and input impedance. If we assumed the input impedance is purely resistive, the input voltage of the amplifier V-in is equal to Vs multiplied Z-in over Z-in plus Rs. This is using voltage divider. In this example, the value of V-in is equal to 6.667 mV. Therefore, the input voltage to the amplifier must be lower than the rated value of the source. The Rs and Z-in on the amplifier input side can affect the input to an amplifier. Let's try one example. Assume that the AV is 100. Find the value of Vout for V-in1 equal to 10 mV and V-in2 equal to 6.667 mV. Straight away we can see that the Vout1 will be equal to 1000 mV and Vout2 will be equal to 666.7 mV, and these are due to the changes in V-in value. And what are the factors that can change the V-in value? For this example, we can say that Rs and Z-in will have impact on V-in value. We can see that the Vout will reduce according to the V-in, and this can be caused by changing the value of Rs and Z-in. Now we look at the output side of the amplifier circuit. When we connect the amplifier with a load resistance, the amplifier will act as the source for the load. As with any source, there is some measurable value of source impedance, and in this case, it is the output impedance Z-out of the amplifier. Let's consider this example. Assume that the Z-out is 300 ohm. The load sees the amplifier as a voltage source with an internal impedance of 300 ohms. If we assume that the output impedance is purely resistive, we can get the voltage at the load equals to Vout multiply RL over RL plus Z-out using voltage divider method. Now, let's put the input side and the output side together and consider this circuit that has a gain AV of 340. We can calculate the value of the V load from the input side by calculating the V-in as follows. First, using voltage divider, V-in is equal to 14.7 mV, and therefore the AVV-in inside the amplifier is equal to 5 V. From there, we can calculate the V load is equal to 4.14 V. From there, we can calculate the effective gain of the complete circuit AVF equal to V load over Vs, and we can get 276, whereas the amplifier gain AV is actually 340. So we can see that the combination of the input and the output circuit can cause a fairly significant reduction in the effective voltage gain of an amplifier. Hence, the effects of the input and output circuit have on the voltage gain of an amplifier can significantly reduce by first increasing the value of Zin and second decreasing the value of Zout. Now we look at the characteristic of an ideal voltage amplifier. The following are the ideal characteristics. First, we want infinite gain AV, secondly, infinite input impedance Zin, and thirdly, zero output impedance Zout. An ideal amplifier would be capable of providing any value of gain, no matter how high the value is, but in reality, the value of AV is limited and the limitation depends on the type of active components used in the circuit. The impedance characteristics of the ideal amplifier are illustrated in the figure. With infinite impedance, there would be no current in the input circuit and therefore no voltage drop across the source resistance Rs. And with no voltage drop, the Vin is equal to Vs, or in other words, the source voltage would not be reduced by the effects of Rs and Zin. On the other hand, with zero impedance, there would be no voltage divider in the output circuit of the amplifier. Therefore, VL is equal to Vout or AVVin, and there would be no reduction of voltage either at the input or output circuits, and the effective voltage gain AVF of the circuit would be equal to the calculated value AV. Now let's discuss about current amplifier. The current amplifier is a circuit designed to provide a specific value of current gain. The general model of a current amplifier is shown in the figure. The current amplifier has input impedance Zin, output impedance Zout, and current gain AI. When we add the voltage source and the load to the current amplifier model, we get the circuit shown. The input side consists of IS, Rs, and Zin, while the output side consists of AI, In, Zout, and RL. Let's look at the difference between the voltage amplifier model and the current amplifier model. We can see that the main difference is at the voltage control source and the output impedance, and the current control source and the output impedance. For voltage amplifier, the voltage control source is in series with the Zout, while for the current amplifier, the current control source is in parallel with the Zout. Meanwhile, there is no difference for Zin or the input impedance where we're considering the location of the impedance. Actually, both the current control source and the voltage control source can be transformed interchangeably using the Norton theorem, which means we can find the equivalent current amplifier model for a specific voltage amplifier model by transforming the circuit from voltage control source to a current control source using Norton theorem, but don't forget the location of the output impedance Zout for both models. Let's consider this current amplifier circuit. The combination of IS, Rs, and Zin from a current divider and the value of the input current In is found by using the current divider relationship. In is equal to Is multiplied with Rs in parallel with Zin over Zin. And for this example, we found that In is equal to 90.9 microampere, which is less than the value of current source or Is, which is 100 microampere. At the output side as shown in the figure, similarly we can find the load current or IL, which is equal to Iout by using current divider. IL is equal to 8.33 mA, which is less than the current control source inside the amplifier, which is equal to 10 mA. That wraps up our discussion on amplifier. I hope you get more knowledge about amplifier characteristic, ideal amplifier conditions, voltage amplifier and current amplifier models, and learn how to solve amplifier circuits. Stay tuned for more video and see you again.